So this afternoon, we're going to hear from Dr. Katie McFall, who's a postdoctoral research associate at Cardiff University, where she runs the Fluid Inclusion Research Lab there. Katie finished her PhD in 2016 at the University of Southampton with a ton of awards and successful research grants. And her PhD focused on critical metal-bearing porphyry deposits, and she has subsequently become a worldwide expert on a variety of deposits, but really focused on critical metals in magmatic hydrothermal environments. She's worked as part of a multidisciplinary study on the cycling and supply of selenium and tellurium, which are invaluable resources for the development of sustainable energy. Currently, Katie is focused on the role of volatiles in the formation of the Bushveld Complex in South Africa as part of the NL4D consortium, which is a project supported by Anglo American. And actually, we at Ore Deposits Hub owe Katie a huge thank you, because actually Katie was the first person to volunteer her time and support by applying to give a talk. So we wouldn't be doing any of this without the participation and effort from our speakers and our participants. And it's really because of you all that this Ore Deposits Hub is even working the way it is. So thank you. With that, I will let Katie speak then and teach us a thing or two about primary volatiles and layered intrusions and their effect on nickel-copper PGE mineralization.
Cool. Well, thank you very much. And thank you very much for having me. As always, with any scientific research, this is by no means a sole effort. So I want to thank all the people who've helped me out with this. I've probably forgotten some people as well. But yeah, so I'm going to talk about primary volatiles in layered intrusions and their effect on nickel-copper PGE mineralization. And I guess I wanted to start by giving a bit of background as to how I came to be interested in this problem. So as mentioned, I did both my undergrad and my PhD at Southampton, and my master's was actually on a copper-nickel PGE deposits, so sort of magmatic sulfides. And then I fled the magmatic sulfide world and did a PhD on porphyry copper deposits, where I did a lot of fluid inclusion work. And just as a contrast to some of the images you're going to see later, this is one of my samples from my PhD. This guy is like 50 microns across. So you can see all these beautiful inclusions. Those are the clearest and largest inclusions you're going to see in this talk, and they're nothing to do with the Bushveld. But anyway, so I guess my background was very much hydrothermal, but I worked on the Skouries deposit, which is a PGE enriched porphyry, and that got me interested in hydrothermal mobilization of PGEs and what happens at the kind of magmatic hydrothermal boundary and at really high temperatures in these brine inclusions. I've just finished a postdoc at Cardiff on the tellurium and selenium consortium, so looking at critical metals, and as part of that, I started working on the northern limb of the Bushveld. And then now, just a month ago, I started on this NL4D project, which I'll talk a little bit about at the end, which is supported by Anglo American. So most of this work was done sort of under the TEES consortium banner, but some of it has been involving the new grant as well. So I'm going to be talking about magmatic nickel-copper PGE sulfide deposits, and I guess just as a bit of a refresher, these are where PGEs are hosted in sulfides and in platinum group minerals, and they've always been traditionally thought of as a dry process, so no role for volatiles. And I guess at its absolute simplest, you have a sort of accumulating crystal mush in a layered octomorphic intrusion, and something causes sulfide saturation, and so immiscible sulfide melt droplets form. These then scavenge metals from the surrounding magma and then cool through a series of stages. So at around 1000 degrees C, you get an MSS, so a monosulfide solution forming, and that's mainly iron and nickel sulfide, and a lot of the IPGs, so like osmium, iridium, rhodium, ruthenium, partition into that. And then at around sort of 900 degrees C-ish, you get, so you have the ISS, which is a copper sulfide liquid, and you start to get, if there are enough semi-metals around, you start to get the formation of an immiscible semi-metal melt, so bismuth and tellurium usually, and this will take most of the platinum, palladium and gold from this ISS and partition it into this immiscible semi-metal melt. And then as the system cools further, this semi-metal melt will crystallize as platinum group minerals, which are normally found within and around the magmatic sulfides. So far, so simple. But what happens if during this process, reactive country rocks are being assimilated? So for example, if you've got a dolomite and that's being assimilated at the same time as we're going through this process, this dolomite would give off volatiles. And so I guess the question I want to answer is there actually a role for volatiles in these so-called magmatic deposits? And this is by no means a new question. People have been looking at this for many, many years, and it's been the source of some quite hot debates. And I'm not going to try and solve all of those debates today, but I guess, again, at its sort of absolute simplest, at one end of the spectrum, there are people who say, no, there's no role for volatiles, and there's no evidence, no real evidence for the role of volatiles in the formation of this type of deposit. It's all magmatic, and there's, volatiles have nothing to do with it. And at the other end of the spectrum, you have some people who say, actually, these deposits aren't really magmatic at all. The metals are being carried by volatiles, and it's all about volatile melt interactions, and that's what's forming these deposits. So in fact, these are magmatic hydrothermal deposits. Now, most people are actually somewhere on a spectrum in between those two sort of endpoints, and myself included. And as I said, I'm not going to try and solve the entire debate today, but instead I'm going to focus on three main questions. So first of all, are primary volatiles actually present during the formation of magmatic sulfide nickel-copper PGE deposits in layered intrusions? A quick sort of terminology note: when I say primary volatiles, I mean volatiles which were present while the system was still at least partially molten. So essentially, we're looking at temperatures of sort of above 800 degrees C. So I'm not going to be talking today about secondary remobilization by low temperature volatiles. I'm only going to be talking about high temperature volatiles. And also, when I'm looking at this question, I'm going to look at direct evidence. So essentially, I'm going to be talking about fluid inclusions. So there's been an awful lot of really good work done looking at, for example, chlorine-fluorine ratios in apatites and isotopic evidence and other things like that. However, if I was to go through all of that, we'd all be here at midnight. So I'm just going to focus on my work, which has been on the fluid inclusions. The next question I want to answer is, what effect does this have on mineralization? And then finally, what are the implications for exploration and processing in these kind of deposits if we do have these primary volatiles present? So I'm going to start off by talking about a case study that I've been working on for a few years now in the Northern Bushveld. Then I'm going to open it up a bit and talk about layered intrusions globally, and then come back to the Northern Bushveld and talk a bit about the future of the research that we are doing. So the Bushveld complex is it's the world's largest layered intrusion, contains around 75% of the world's PGE resources. And to just show how large it is, if I was to put the Bushveld complex on top of the UK, it would cover all of England and Wales pretty much. So it is really big. And the magmatic sulfide deposits in the Bushveld generally host their PGEs in sulfides, chromites, or in platinum group minerals. So this is a very basic geological map of the Bushveld, and essentially it has the western limb, the eastern limb, and the northern limb, which is what I'm going to be talking about mainly. And there are sort of various crude, I guess, stratigraphic units. So the lower and critical and marginal zones here in red are generally the more ultramafic ones, so kind of like peridotites and things. And then you have the main zone, which is slightly more leucocratic, so you're looking at gabronorites to anorthosites, and then the upper zone, which is more anorthosites and magnetite layers. And at Cardiff, we've done a lot of research on the northern limb, and the northern limb is of increasing interest, both in research circles, but also economically. And one of the reasons is its unusual metal tenors. So this is a figure that Ian McDonald put together. And these are all of the magmatic sulfide deposits in the Bushveld, and it's the palladium, platinum, gold proportions of their published resource. So in the western limb, the eastern limb, and then up here in the northern limb. And what we can see in the northern limb is actually these deposits are palladium dominated. So most of the rest of the Bushveld is predominantly platinum, but the northern limb is predominantly palladium. And as I'm sure a lot of you are aware, palladium price has only been going up and overtook platinum a little while ago. And in fact, often is around about the same price as gold. So this is of great interest for exploration at the moment. Another reason why the northern limb is of interest economically is that the deposits are quite shallow. So the Platte Reef, for example, is one of the world's largest PGE deposits. It's this dotted red line on this crude geological map here. And And Mahalajuena is actually currently, I think, the world's largest open pit platinum mine. So in places, these things are shallow enough that you can open pit mine them, which again makes them very attractive economically. But from a research point of view, the Northern Limb is also very interesting. So one of the other differences between the Northern Limb and the rest of the Bushveld is that the Northern Limb intrudes reactive country rocks. So again, in this geological map, so this is the Northern Limb, these are the granites, this is the upper zone, the main zone in dark green, and then this sort of blue stippled bit here is Malmani dolomite. So the Northern Limb intrudes the Transvaal sediments, and particularly the Malmani dolomite, and there's a lot of dolomite assimilation throughout the whole strike length of the Northern Limb, which makes it the perfect place to examine this question of what happens if there are volatiles around while these deposits are forming. The other interesting thing about the Northern Limb is that unlike the rest of the Bushveld, the deposits aren't all hosted in the critical and lower zones. So the main zone, and perhaps even the upper zone, so these are our gabronorites and leucogabbronorites and anorthosites even, can contain nickel-copper PGE deposits. And again, in terms of the Bushveld, this is quite unusual. And so I'm going to be talking mainly about the Aurora project, which is up to the north here. And it's a nickel-copper PGE deposit, mainly platinum, palladium, and gold. And it's one of these deposits which is hosted in what's interpreted to be the main zone. So it's hosted in gabronorites. It's also unusual in that the mineralization is copper and gold rich, and that it doesn't contain much chrome at all, and there's no relationship between the PGE mineralization and the chrome mineralization. And to be honest, this was the main reason why we started looking at Aurora when we started this research project. We weren't really thinking about volatiles. It makes a nice story for this presentation, but actually we were more interested in why is there PGE up in the main zone, and the volatile discovery was almost kind of a happy accident, although I suppose I shouldn't really admit that. But very briefly, the geology of Aurora. So it has three broad units. Unit 1 is peridotites, and then Unit 2, which is where the majority of the PGE mineralization is gabronorites and leucogabbronorites, and then it goes on up into pigeonite gabronorites, which are barren. And it also contains calc-silicate xenoliths, which shows that dolomite was indeed being assimilated during this deposit formation. So what does the mineralization look like? Well, as expected for a magmatic sulfide deposit, there are magmatic sulfides. So we have blebs of sort of what we call primary magmatic sulfides. So these are pentlandite, pyrrhotite, chalcopyrite, which is kind of your classic assemblage, and these form as blebs in silicate. However, there are also a significant amount of what we've sort of defined as secondary hydrothermal sulfides. So these are mainly chalcopyrite and pyrite, and they're hosted in hydrothermal alteration minerals, so quartz, for example, or chlorite, or in cracks between primary magmatic silicates. And so this was kind of our first clue that maybe hydrothermal processes might be important in this deposit. Having done some laser ablation on these, it turns out that actually, even though this is a platinum, palladium, gold deposit, platinum and gold were below detection limit in all of the sulfides analyzed. And so palladium was the only PG which was detected, and even the palladium was in very low concentrations. So this is a histogram showing palladium and pentlandite from the Rensky Reef in gray, the Platte Reef in blue, and then Aurora in red. And you can see that the pentlandites in Aurora have much less palladium in than the rest of these Bushveld deposits. Now, as I said, this is an economic deposit, so it just means that the PG grade must be in platinum group minerals rather than being in the sulfides. And indeed, whenever I did a platinum group mineral survey, yes, there they are, happy days. But when I started looking at where exactly the platinum group minerals are hosted, again, this was where we found something quite interesting. And I'm going to quickly shamelessly plug, this is all in the sort of mineralization section is in a paper that was published in March last year on Aurora Geology reviews. And if you want a copy, just drop me a line. So we found whenever we looked at where the platinum group minerals are, we found only 25% of them were in the sulfides. So if you remember back to my traditional magmatic sulfide formation process, almost all of the platinum group minerals should be in and around the sulfides. But in fact, only 25% of them are touching sulfides in this deposit. 23% of them are in alteration halos around the sulfides. So here are platinum group minerals, and this is a chalcopyrite, I think. but actually 52% of them are spatially removed from the sulfides. So these are platinum group minerals, and they're hosted in hydrothermal alteration minerals, so things like quartz, chlorite, or actually just in cracks within primary magmatic silicates. Now, when I'm talking about spatially removed, I'm not talking about meters. It's sort of on a assay level, the sulfides and the PGM do still relate to each other. So it's not moving them meters and meters away, or at least we don't think so. But certainly there are never any sulfide, or well, there are often not any sulfides within the same field of view as the platinum group minerals. And this has obvious processing implications as well. So why is this the case? Well, as far as the sulfide-hosted platinum group minerals are concerned, these likely formed just through sort of the traditional cooling of a immiscible sulfide melt. As far as the sulfide halo-hosted platinum group minerals are concerned, there was a really nice paper by Dave Holwell et al. In 2017 looking at the effect of low-temperature hydrothermal alteration on sulfides, and they found that actually low-temperature hydrothermal fluids cause volume shrinkage of sulfides. So essentially, you have your original sulfide, and then during hydrothermal alteration, the volume shrinks, and the platinum group minerals are kind of stranded in an alteration halo around it. And I think you can sort of see that here. So if we imagine that the original boundary of this sulfide was actually out here, what's happened is this all here is chlorite, and so basically this sulfide has shrunk and sort of stranded these guys here. So these platinum group minerals probably were formed sort of, again, originally within the sulfide. However, what about the 52% of them which are nowhere near the sulfides? So they're not close enough to sulfides for that volume shrinkage to have occurred. They are spatially removed. And so this suggests that they've been remobilized. So I guess there's two options. It could be secondary low temperature fluid remobilization, or it could be that this was a primary volatile, so a fluid phase, a volatile phase, sorry, that was present while the system was still partially molten, that then removed the PGM from the sulfides. And I guess there's two options for those volatiles. They were either given off as the dolomite was assimilated, or they're primary magmatic volatiles from fractionation of the host intrusion. And so in order to find out which is which, we wanted to look for some fluid inclusions. And the really cool thing about Aurora is there are actually fluid inclusions present, not just in secondary quartz, but also in primary magmatic silicates. So cumulate plagioclase, intercumulus orthopyroxene, and olivine all contain fluid inclusions. And these are commonly associated with melt inclusions and sulfides. And it's these fluid inclusions that I'm going to talk about for the next little bit. So what do these inclusions look like? Well, the vast majority of them are brine inclusions. So here are some nice pictures. First of all, I should point out that all of these inclusions are really small, and this has made it analytically slightly challenging. I'm normally very happy if I see a 10 micron inclusion, which I guess if you compare that to that porphyry inclusion photo I showed at the beginning, yes, my life has got a lot more high magnification. But they are there, and we can begin to pick out some of the features. So they have an awful lot of daughter minerals. In fact, a lot of them look almost verging on salt melt inclusions, and all of them contain halite. You can also identify iron magnesium carbonate, iron chloride in some of them. So this little trail here, I don't know if you can see, but right about there is actually some hematite. Now I suspect that originally that would have been magnetite, and hydrogen diffusion over time has oxidized it into hematite. So I'm not saying that this is a highly, highly oxidized fluid, but certainly there would have been magnetite in these. And there are also obviously vapor bubbles, and you can see some liquid as well. There are also some other types of inclusions present in Aurora in the primary magmatic silicates. So there are vapor inclusions. So here, for example, we have a little halo of vapor inclusions around a chalcopyrite crystal within a feldspar. And also there are pure salt melt inclusions. So some of them are sort of polyphase salt melt inclusions, and some of them are just little halite crystals sitting in a feldspar. And when I heated this guy up, it actually melted bang on the melting point of halite, which was quite nice. So I guess the first question whenever I was looking at this is, whenever I was looking at the vapor inclusions, is what are the what vapors are they? And so I was lucky enough to be able to visit St Mary's University in Halifax and do some work with Jake Hanley on the really nice high-resolution Raman to have a look at this. And I must admit, I was assuming that they were going to be carbon dioxide because most, when you think what vapor phase is going to be dominant in a layered ultramafic intrusion, it should be carbon dioxide. Actually, I didn't find any carbon dioxide in any of the inclusions that I analysed. In fact, all of the vapor inclusions were methane and nitrogen. So I would love in the discussion at the end if anyone has any ideas as to where those might be coming from. There is a small amount of shale at the bottom of the Malmani dolomite, but the sulfur isotopes in Aurora show bang on magmatic values. There's no evidence of any sulfur input from shale. So if the nitrogen is from a shale, you then need a way of not having any of the sulfur from the shale. And I guess the other question here is what actually happened to the carbon dioxide? Because if we are assimilating dolomite, you'd assume that would give off carbon dioxide. Equally, if these are magmatic volatiles, again, it should have carbon dioxide. And I suspect that part of this might be to do with wetting. So aqueous fluids can wet to silicate crystal surfaces much more easily than carbon dioxide, and so are more likely to be preserved by fluid inclusions. So perhaps the carbon dioxide all just streamed through and was degassed, or it could be that the initial magma was actually carbon dioxide undersaturated, and so it all dissolved into the melt rather than being trapped as an immiscible volatile phase. So that was the first thing from the Raman. And then the other interesting thing found from the Raman is, so these sort of brine inclusions here, first of all, they are aqueous brine inclusions, thankfully. Because certainly at that kind of level of magnification and number of daughter minerals, it can be very easy to mix up melt and fluid inclusions. But the brine inclusions, they do have liquid water in them. They also have halite, magnesium carbonate, but a lot of them also contain sort of magmatic daughter minerals, so things like clinopyroxene or diopside. And this suggests that actually a lot of them are hybrid brine melt inclusions rather than just pure brine inclusions. And this suggests that these brines, this hypersaline hydrous fluid, was around at the same time as a melt. So we potentially have an immiscible brine and silicate melt at the same time. And this is good evidence that indeed these are primary volatiles, which was present while the system was molten. We can also see some of this evidence just looking through the microscope doing some fluid inclusion petrology. And I guess at this point, I wanted to take a quick aside to say that whenever you're looking at fluid inclusions in these systems, there are a few differences to looking at fluid inclusions in hydrothermal quartz veins in, say, a porphyry deposit. So as any of you have done fluid inclusion studies, well, I've probably seen this diagram many, many times, but one of the main things you try and do when cataloguing fluid inclusions is decide whether they're primary or secondary. So a primary fluid would be trapped along a growth zone. So this is a cartoon of a quartz crystal. And that means that that fluid was present while this crystal was growing. And of course, in a hydrothermal quartz crystal, it's likely that this is the fluid that the crystal is actually precipitating from. Now, obviously, in an ultramafic intrusion, I'm not saying that these are hydrothermal orthopyroxenes. So that's sort of one big difference to begin with. The brines which are being trapped in these primary magmatic silicates are representing an immiscible volatile phase. They're not representing necessarily the phase that this crystal crystallized from. Also, preservation is an issue. So as I said, they're very small, and we don't really see, I've seen a few in feldspar, but they're very, very rare. And I suspect that's because if you have a brine inclusion in a feldspar, after a certain amount of time, it's just going to react with the feldspar and you'll be left with just a little patch of alteration. However, we do find that preservation is pretty good in orthopyroxene and in olivine. And so when I'm looking at inclusions in orthopyroxene and olivine, generally I find that it's most useful, they're mostly in trails, and it's most useful to look at the trails in terms of crystal boundaries rather than necessarily growth zones, because it can be very difficult to try and identify growth zones in for example, a slightly altered olivine. So this is a cartoon from Kirchhoff and Hines fluid inclusion petrology paper. And I think this is supposed to be quartz crystals, but we're going to pretend for a minute that this is an ultramafic intrusion and that these are orthopyroxenes and olivines, for example. And so whenever we're looking at inclusions in this setting, if the brine trail is like trail 1, then simple cross-cutting relationships show that this brine must have been present after all of these crystals solidified, because it's cross-cutting all of the crystal boundaries. Brine trail 3 here is within a crystal. Now, because it's in a trail, that suggests it's in a healed fracture, which means this crystal was probably at least mostly solid whenever this brine was present, but we don't know how that brine relates to the other crystals around it. Brine trails number 5 here, though, they terminate against the crystal boundary, which would suggest that this crystal had solidified, but the crystal next to it hadn't solidified at the point that these brines were trapped. And this means that we can use these kind of cross-cutting relationships to begin to get an idea of the timing of exsolution of volatiles in these systems and when these brines might have been around. So here's some brines in an orthopyroxene crystal in Aurora. And this is at 50 times magnification, and this is at 10 times magnification, so it's the same assemblage. And you can see that here, it's quite difficult to see the relationship of this with either the crystal growth or with the surrounding crystals. So I mean, if I wanted to, I could probably claim it was primary if I wanted to define this as a growth zone, but I'd probably get into trouble for that. But all I can definitely say is that these brines were trapped either as this crystal was growing or just after. However, in something like this, here we have an orthopyroxene crystal, and here we have a clinopyroxene crystal, and here we have a little trail of brines that cross-cut this orthopyroxene and terminate against the boundary with this clinopyroxene. And so this suggests that these brines, this brine phase, which has been trapped here, was present during or soon after the growth of this orthopyroxene crystal, but before this clinopyroxene was crystallized. And again, textures like this show that it is likely that these brines were around while the system was still at least partially molten. But of course, I guess that the best way would be to find out what the temperature of these fluids actually are. And so I've been doing microthermometry on these. And again, their size makes it a little bit difficult, but I have been able to get some data out of these. So these are box plots showing the homogenization temperature of fluid inclusion assemblages within plagioclase, olivine, and orthopyroxene in the Aurora deposit. And the first thing to take away is that all of them homogenize above about 830 degrees C. And so homogenization temperature here is a minimum trapping temperature. So that means that these volatiles were originally at least 800 degrees C, and more likely higher temperature depending on what the pressure was at the time that these were trapped. The other thing, I guess, getting a little bit more tenuous here, but you can begin to have a think about, so in the Aurora deposit, plagioclase crystallized first, followed by olivine and orthopyroxene, and it does, certainly between plagioclase and orthopyroxene, there does seem to be a drop in temperature of the trapped volatiles, but well, yeah, with the eye of faith. Perhaps unsurprisingly, given the number of daughter minerals, these are also very, very high salinity. So they're all above 60 weight percent NaCl equivalent. And I guess the most important point from all of this talk about brine inclusions is, I guess, if you only take one thing away from this, is that these are really hot, really salty fluids, and experimental work has shown that these types of fluids can carry metals, including potentially PGE and certainly gold and palladium. So whenever we're thinking about the formation of our deposit, we now know that there was a volatile phase present which can carry metal while this deposit was forming. And we can start to use these temperatures to think about what temperature the fluid was actually originally at. So as I said, homogenization temperature is a minimum. Unfortunately, we don't know what the depth of the Aurora deposit was when it was formed, but a trapping pressure of around 150 MPa is probably reasonable. And that gives an estimated fluid temperature of between 935 and 1080 degrees C. So in terms of hydrothermal fluids, these are really, really high temperature. These are going to be incredibly corrosive because they're very, very saline. But more importantly, it means that we can put this into context of what our sulfide melt would be doing at the time. So again, going back to this lovely diagram from Howell and MacDonald, at between sort of 900 and 1000 degrees C, at this point, the MSS would be solid. So our iron nickel part of this sulfide melt would be solid, but the copper-rich sulfide liquid would be at least partially molten. And perhaps more importantly, our semi-metals, our semi-metal immiscible melt, so our bismuth tellurium melt, which is where most of our gold and palladium is, will be separating and will still be liquid at this point. So it'll be very, very available for remobilization by our very aggressive fluid. Now, I'm not going to get too much into the sort of silicate geochemistry of this, but I've started to do a bit of modeling to see what the crystallization state of the intrusion would have been at the temperature that these fluids were present. And sort of very, very rough, but paleomodeling has suggested that actually at this point, the host intrusion of the host rocks would be between 80 and 95% crystallized. Now, this is actually quite good news, because one of the big problems with volatiles in layered ultramafic intrusions is the relative viscosities, and how do you move an aqueous fluid a long distance within a crystal mush. And so one of the suggestive ways that this can happen is through a fluid network. So potentially, as there's quite a lot of crystals formed, this aqueous fluid could wet to the crystal boundaries and form a sort of network of fluid, and then this would interact with this immiscible sulfide melt, remobilizing our platinum group minerals, either by physically removing the immiscible semi-metal melt, or by dissolving some of the sulfide, some of this ISS, and then as the system cools, these would then precipitate as platinum group minerals within the silicates, giving us this texture we see where we have platinum group mineral blebs within hydrothermal alteration minerals like quartz. So I guess that's the first part of my talk is about Aurora, and I guess the take home from this is that in Aurora we've seen that there are fluid inclusions in cumulate magmatic silicates, and that these fluids were highly saline, very high temperature, and therefore capable of carrying metals, and they were present while the system was still at least partially molten. And in Aurora, we see from the mineralogy of the ore that actually, indeed, the precious metals have been remobilized, and the PGE and gold have been removed from the sulfides and instead are hosted in hydrothermal alteration silicates, which has important implications for processing, seeing as the PGM are essentially in the gangue. So that's just Aurora, and I guess the question there is this just a nice little local story, or actually have fluid inclusions been identified in cumulate silicates in any other layered intrusions? So first of all, what about the rest of the Bushveld? Sorry. There have been various sort of reports of fluid inclusions in the main. So I'm talking about sort of the western and eastern limb of the Bushveld. So in dry cup, for example, some very, very highly saline, in fact, liquid absent at room temperature inclusions were reported. And there has been some work done on quartz and pegmatites around the Merensky Reef. And again, there we see hypersaline brines and also vapor inclusions. Here they have the CO2, which I seem to be lacking in Aurora, however. So there potentially are some more in the rest of the Bushveld. But I now want to talk briefly about the Stillwater Complex. We're going to leave South Africa for a minute and travel across to the USA. Who says you can't travel during lockdown? And we're going to look at this layered intrusion, which is in Montana. And so much like the Bushveld, it's a layered ultramafic intrusion with an ultramafic series and then some upper series which consist of banded anorthosites and gabronorites. And the main sort of mineralization in the Stillwater complex is the JM Reef, which has been said to be, or sort of suggested to be similar to the Merensky Reef. And Jake Hanley et al. In 2008 actually reported that there were fluid inclusions present not only in quartz, but also in orthopyroxene and olivine around the JM Reef. And so these inclusions, hopefully these kind of pictures are beginning to look a bit familiar. Here we have hypersaline brines. They reported some hybrid inclusions, so brine and melt inclusions, or magmatic silicate crystals within fluid inclusions. They also had carbon dioxide, methane, vapor inclusions as well. And the brines in the olivine had homogenization temperatures of sort of 480 to 800 degrees C, so a little bit cooler than we're seeing at Aurora. But they're also very, very saline, and so these were interpreted to be magmatic hydrothermal fluids. And in fact, they were also suggested to have carried metal as well. Now, the interesting thing about Stillwater is, unlike the northern limb of the Bushveld, Stillwater does not intrude reactive country rocks, so there are no dolomites within the footwall. And so this begs the question is actually, do we need reactive country rock in order to produce these volatiles? So if we're seeing the same kind of fluids in an intrusion which doesn't have these dolomites, do we actually need the dolomite, or are the dolomites a bit of a red herring? And in fact, almost or any layered ultramafic intrusion could contain these primary volatiles. There's also been some other interesting work done on volatiles in Stillwater. So Alan Boudreau and his research group have done a lot of work looking at the upper part of the Stillwater complex. And one of the interesting things is that olivine actually reappears. So the upper banded sequences are northicites and gabronorites, and I guess in a sort of classic layered ultramafic intrusion, you shouldn't really have any olivine crystallizing by the time you're into gabronorites and anorthosites. And also, however, in Stillwater, there are troctolite layers, so that's an olivine feldspar rock, and there's no evidence of new melt injection. And so Alan and others have done a lot of melts modeling and actually showed that you only need a very small amount of water to be added to a gabronorite melt in order to generate olivine. And so essentially that's done by stripping out some of the silica and taking it from the orthoperoxene stability field into the olivine stability field. And this olivine is, and so it's been suggested that perhaps in the upper Stillwater, what you have is lower anorthosites are degassing magmatic volatiles, and these interact with gabronorite melt in order to create this sort of metasomatic olivine, if you will. And these olivines have a really interesting kind of interstitial texture, often with orthoperoxene reaction rims around them. Now, I guess I should say at this point, this is only one potential theory for how this could have formed. And the other thing that volatiles are suggested to have done in the Stillwater complex is that there's reverse zoning of plagioclase. So once again, metasomatism by the removal of silica can create reverse zoning in plagioclase. Now, the reason why I'm sort of talking about this is that we actually see some of these features in Aurora as well. So the Aurora deposit also contains reverse zoned plagioclase. So this is an element map from our SEM EDS. And so these here is pyroxene, and then the blue here is plagioclase, and the light blue has lower anorthite numbers, and the darker blue have higher anorthite numbers. And so I did some microprobe work to find out what the anorthite numbers are. And the cores of these plagioclase have anorthite numbers between sort of 70 and 74, and the rims between about 78 and 82, which is the opposite way around to the way you would expect in just a normal fractional crystallization sequence. And it's very similar, once again, to what they see in Stillwater. Similarly, in Aurora, so this is our so these sort of yellow and grey bits of the stratigraphy are gabronorites, and this red horizon here is an olivine gabronorite horizon. So again, we see the reappearance of olivine within a gabronorite sequence. And the olivines here, again, have a really weird kind of almost interstitial texture. And so potentially this could be metasomatic olivine. This could be due to the addition of these volatiles to the melt. And indeed, if you remember, we do see brine inclusions in olivine in Aurora. They've got homogenization temperatures of, I think, about 80 to 1000 degrees C. And actually, there's some really, really neat textual information to be had in these olivines. So this is, again, an element map showing olivine in light green, and in the dark green is an orthoperoxene reaction rim, and the purple here is plagioclase. And this is a close-up cross-polarized light of the same crystal. And so here we have the olivine, here we have the orthoperoxene rim, plagioclase, and then here you can see there's a trail of brine inclusions that cross-cuts the olivine, which terminates against the orthoperoxene reaction rim. And this is a different crystal, but again, brine inclusions trail that terminates against orthoperoxene. And so we can begin to pin down the timing of these brines. So this means that these brines must have been present probably after the olivine crystallized, because they're in a trail across it, which means there must have been something to fracture in order to host them, but certainly before this reaction rim was formed. And so once again, these brines were present while the system was still very hot, and while the sulfides would still be at least partially molten. So interestingly, there's also another unit in the northern limb, is the Troctolite unit. So much like in Stillwater, in the main zone of the northern limb, which is gabbronorite mainly, we have a layer of Troctolite, so olivine feldspar rock. And Bianca Kennedy, who finished her PhD at Cardiff last year, did her PhD on this, and she found out that there's actually PGE grade in the Troctolite as well. So this is just from Bianca's thesis, and so yeah, here's the stratigraphy of the Troctolite unit, and you can see that there are little kicks in the PGE and gold grade. And again, you have this really interesting olivine texture, so this kind of interstitial olivine with orthopyroxene reaction rims. And Bianca actually noted in her thesis that there were some fluid inclusions here as well. So this is the same sample. This is an element map, so showing olivine and orthopyroxene surrounding it. And then this is in cross-polarized light. Here's the olivine crystal, here's the orthopyroxene, and here you can see there are brine inclusions cross-cutting the olivine, and once again, terminating against the orthopyroxene. So once again, we can pin it down. There was a brine present before this orthopyroxene crystallized. And actually, currently what I'm working on at the moment is I'm looking at some of Bianca's samples and looking at these brine inclusions, and hopefully we'll be able to get some temperatures on those soon. And sort of just to finish it off, I haven't really talked much about the Platte Reef, but again, these are some photos from a master's project done by Eva Marquise at Cardiff, and you can see these really weird olivine textures, these kind of almost interstitial reaction textures. And so I guess the question is, can we take these sort of interstitial olivines, if you will, as an indication that there were primary volatiles present? Because doing the fluid inclusion surveys is very, very time consuming. And so it would be useful if you could pick up a piece of core and go, oh, look, interstitial olivine, there must have been volatiles. Maybe my PGEs have been remobilized. And so that's certainly something to think about for the future. So to go back to my initial 3 questions, first of all, are primary volatiles present during the formation of these magmatic sulfide deposits in layered intrusions? Well, I think we can say certainly at Aurora, yes. So primary volatiles have been identified as fluid inclusions in magmatic silicates in several deposits across the northern limb, also in the Stillwater Complex. And as I said, there are reports of fluid inclusions elsewhere in the Bushveld as well. So I suspect there may well be more of these things out there than we think there are. What effect does this have on mineralization? Well, these volatiles, they're very high temperature, they're very high salinity, and they are perfectly able to transport metals and potentially PGE as well. And these fluids were around while the system was still at least partially molten, and certainly in Aurora, the fluids remobilize PGE away from the sulfides. And then finally, especially those of you who are from industry might be sitting there thinking, that's all very nice pictures, but what's the point? What are the implications for exploration and processing? Well, first of all, processing-wise, as I said before, in Aurora, the PGEs are actually not in the sulfides, they're in the gangue. And so there are obvious problems there for geometallurgy. Similarly, if you've got a large amount of fluid flow, so if you've got loads of volatiles streaming through this, and they're all high temperature, high salinity, it potentially could be grade destructive. So it could be stripping out some of the metals from our sort of nascent magmatic sulfide deposit. Similarly though, if a fluid has been streaming through a forming magmatic sulfide deposit, taking all the metals away, that actually makes a really good source for secondary hydrothermal PGE and nickel and copper deposits. So for example, the hydrothermal Waterberg deposit in the Bushveld, or some of the Sudbury footwall deposits, could potentially be the end product of this process. And certainly if we think that these volatiles are coming off the country rock, then country rock type and proximity to xenoliths could be really important for exploration and grade control. And as I said, if this link between these kind of interstitial olivine textures and the presence of primary volatiles does hold true, then that would give a really easy sort of first pass look idea as to whether these things might have been present or not. So I guess what's going to happen, I guess I just wanted to quickly say sort of what's happening with this going forwards. Here's Aurora, which I've been talking about today. The Waterberg deposit is just to the north, and actually Aurora has been suggested to be a continuation of the same mineralized horizon. And so I'm currently working on a project in collaboration with the University of Witwatersrand looking at Waterberg samples to see if there are fluid inclusions there and how the system there compares to the system at Aurora, because interestingly, Waterberg doesn't actually intrude any dolomites, whereas Aurora does. And then, as I said at the beginning, I've just started on a new grant at NL4D, which is a consortium grant between Cardiff, Leicester, and Exeter, and Anglo-American, looking at making a holistic model of mineralization across the northern limb. And I guess my part of that is looking at this question of where are volatiles, how do the volatiles relate to the xenoliths, how does alteration relate to grade, and things like that. So watch this space for a bit more information on these open questions. And I guess kind of the open questions that for me certainly, I'm sure there'll be lots of other questions as well, but for me certainly the open questions are, or the sort of most important open questions here are these volatiles actually from the country rock, or are they from magmatic degassing? And this is important because if they are only from the assimilation of dolomites, then that means we only need to worry about this in layered intrusions that actually intrude reactive country rocks. Whereas if they're from magmatic degassing, that means that these volatiles could be present in any layered ultramafic system. How far can volatiles move in these systems? So in Aurora, it doesn't look like the metals were remobilized that far. We're only talking about sort of centimeters. But is it possible that volatiles might be remobilizing metals by meters or even kilometers? And there's been a lot of work done on looking at sort of fluid dynamics in these systems. And again, sort of opinions range from they can't move at all, they're trapped where they form, to they can move for kilometers and kilometers and they can go wherever they want. So I think, you know, we still need to pin this down a bit. And also the dynamics and I guess the geochemistry of metal transport. Again, there's still a lot of debate over particularly platinum, whether it can in fact be moved by hydrothermal fluids or not. I would probably argue that it can, but that's still an open question. And then also, as I said, how widespread are these volatiles? Are they actually present everywhere? And it's just the case that we haven't looked for them. And there's a lovely quote from Goldstein's chapter on fluid inclusion petrology in one of the short course books that I think sort of applies here, which says that a fluid inclusion study requires patience and oftentimes the spirit of a gambler. After searching 20 samples and finding no useful inclusions, you always wonder about 21. Is that the one that will have the beautiful fluid inclusions you need? And I wonder if there's an awful lot of 21, you know, sample number 21s out there that might actually have things like this in them that just haven't been sort of recognized for what they are. So I guess if I was to summarize this talk in one sentence, I would say primary volatiles can remobilize metals in layered intrusion hosted nickel-copper PGE mineralization and are probably actually a lot more common than we think. So thank you very much, and I'd love to answer any questions that you might have.